Continuing with diagonalizing matrices. Here's a 3 by 3 matrix. We want to diagonalize if possible. So first of all, we're going to find eigenvalues, and it's going to be really easy to find eigenvalues here. Find eigenvalues. It's not even writing. So finding the eigenvalues of A, we're going to take the determinant of A minus lambda, so it's the characteristic polynomial, I, set it equal to 0, and lambda's in place of the normally where you have an x. So what do we got? We got 3 is the main diagonal, 3, 3, 3. We're going to subtract lambda from each of those. We're going to get the determinant of, now what is that going to be? 3 minus lambda, 3 minus lambda, 3 minus lambda going down the main diagonal. And everywhere else stays the same. This is all equal to 0, of course. We're going to have 1, 0, 1, and then 0 is below the main diagonal. So we have another upper triangular situation, which makes life easy. Its determinant is really easy. We just take the product of the main diagonal, 3 minus lambda, 3 minus lambda, 3 minus lambda. That's equal to 0. So we're going to have lambda equals 3. And that's going to have multiplicity. It's going to be 3, right? We have a single eigenvalue repeated. Repeated 3 times, so the multiplicity is 3. It's called the algebraic multiplicity. Algebraic multiplicity. So what we have to do to see if we can diagonalize this is to see if we can, we would want 3 linearly independent eigenvectors. You need n linearly independent eigenvectors to determine if it's diagonalizable. All right, so let's see. We want to look at this eigen. Oh, don't do that. Nope. We're going to look for find a basis for the eigenspace E3 of A. Right, the eigenspace associated with the eigenvalue 3. Right. So let's look at A minus 3I augmented with the 0 vector, right? This is essentially our homogeneous equation, A minus 3I3 times x equals to 0 vector, except we're putting it in an augmented form. So we're going to go to A, and we're going to subtract 3 off of the main diagonal. We're going to have the 0 vector on the right-hand side. So what's A minus 3I3? So subtracting 3 from the main diagonal gives us a bunch of zeros. And everywhere else we're going to have zeros. So these guys are going to be 0 the main diagonal, 0 everywhere else. Why 0 everywhere else? I don't know. Everything else is the same. I don't know why I said 0 everywhere else. So you should have what? 1, 0, 1. And then here, 0, 0, 0. Okay, so we just subtracted the eigenvalue 3 from the main diagonal. Now, if you look at this and you want to find a general solution, come on, man, work. You notice that you have a free variable here in the first column, so x1 is going to be free. That's kind of unusual. If you look at this last here, that's going to tell you that x3 is 0. And to find x2, you can look at this guy, this first row. It's going to tell you that 1x2 is equal to 0. So when you're looking at the vector form of the solution, vector form of the solution to this homogeneous linear system, we're going to have a vector x equals, literally, x1, 0, 0. And if we factor out the parameter x here, we're going to have, what, 1, 0, 0. So here we have a basis for this eigenspace basis for, what's that called? E sub 3 of A? The eigenspace of A associated with the eigenvalue 3. We're just going to call it B for basis. It's the only basis we're going to have because we only have one eigenvalue. It's just going to consist of one vector, 1, 0, 0. So that's the only basis that we have. We only have one eigenspace, right? The eigenspace associated with the eigenvalue 3 of A. We only have one linearly independent vector. Remember, when you're diagonalizing something, you need 3 linearly independent vectors. So we're going to state here, note, A is not diagonalizable since A does not have 3. Let's put it that way. A does not have 3 linearly independent eigenvectors since A does not have 3 linearly independent eigenvectors. We only have one, right? So you have to have 3 when you're dealing with a 3 by 3 matrix. Yeah. So it turns out a condition for diagonalizability is that the algebraic multiplicities have to be equal to what are called the geometric multiplicities. So here, the algebraic multiplicity of 3, right? We have the algebraic multiplicity of 3. That was repeated, right, 3 times. So the algebraic multiplicity of 3 is 3. The geometric multiplicity of 3, this is called the algebraic multiplicity of lambda equals 3. Then there's something called the geometric multiplicity of lambda equals 3. And this is actually defined to be the dimension of the eigenspace of 3. The dimension of the eigenspace of 3. So these would have to be the same. What's the dimension of the eigenspace? It's 1, right? There's just only one basis vector for it. So in order to have diagonalizability, all the multiplicities for every eigenvalue have to be the same as all the geometric multiplicities. And notice that these are not the same, right? That's another way to state it. But I mean, that's actually equivalent to saying that you don't have all the linearly independent eigenvectors you need, right?